The cosmos is not simply vast, it is actively growing. Every galaxy, every star, every point of empty space is stretching away from every other point. And this expansion is the single most important story our universe is telling. Yet, for all we have learned, the deepest truths about this grand narrative remain locked away, posing questions that challenge the very foundations of physics. By the end of this journey, you will understand the 25 most profound and unsolved mysteries surrounding the universe's expansion. We will confront a force that makes up most of reality, but is completely invisible, debate whether space itself might one day tear atoms apart, and uncover a measurement so baffling it hints at entirely new laws of nature. What does it feel like to stand at the edge of human understanding, looking into the dark? Our journey begins with the greatest embarrassment in modern cosmology. We have a name for the force driving the universe apart, but we have no idea what it is. We call it dark energy, and this single, simple label hides a chasm of ignorance. Its story starts not with a theory, but with a shocking observation. In the late 1990s, two independent teams of astronomers were studying distant supernova, the titanic explosions of dying stars. They expected to see the expansion of the universe slowing down over time, pulled by the relentless grip of gravity. Instead, they saw the opposite. The most distant explosions were fainter than they should have been. This meant they were farther away than anyone predicted. The universe's expansion was not slowing, it was speeding up. It was as if you threw a ball into the air, and instead of falling back down, it shot away from you faster and faster into the sky. This discovery was so profound it earned a Nobel Prize, and it introduced the central character of our cosmic drama, dark energy. So what is this mysterious force? In the simplest terms, dark energy is the name we give to whatever is causing the acceleration of the universe. It acts like a kind of anti-gravity, a repulsive pressure woven into the fabric of space itself. Think of the universe as a loaf of raisin bread baking in an oven. The dough is space and the raisins are galaxies. As the bread bakes, the dough expands and every raisin moves away from every other raisin. Now imagine if the yeast in the dough suddenly became supercharged, causing the loaf to swell at an ever-increasing rate. That supercharged yeast is dark energy. Its most peculiar property is what physicists call negative pressure. While normal matter and energy pull things together through gravity, dark energy pushes things apart. It is a stretching force inherent to empty space. The more space the universe creates through expansion, the more dark energy there seems to be, leading to a runaway effect. When faced with this bizarre behavior, physicists turn to a very old idea, one that Albert Einstein himself had proposed and then famously discarded. In his equations of general relativity, Einstein included a fudge factor he called the cosmological constant, a kind of energy density of the vacuum of space that could counteract gravity and keep the universe static. He later called it his greatest blunder when Edwin Hubble discovered the universe was actually expanding, but the supernova observations resurrected this idea. Perhaps Einstein's blunder was actually a stroke of genius, and the cosmological constant is real, representing the dark energy that fills the void. This seems elegant, but it leads to a colossal problem. When we try to calculate how much energy the quantum vacuum of empty space should have, our best theories predict a number that is off by a factor of 1 followed by 120 zeros. It is the worst prediction in the history of science. This means either our understanding of quantum physics is catastrophically wrong, or dark energy is something entirely different from vacuum energy. We are left with a placeholder name for 70% of the universe's total energy budget, a force that dictates the ultimate fate of everything, and we cannot explain it. This is not just a mystery, it is a fundamental crisis in physics. And if dark energy is not what we think, what other surprises does the expanding universe hold? The sheer scale of that error forces us to ask a much deeper question. Is dark energy truly constant, or could it be evolving? This is not a minor technicality. The answer determines whether the universe has a simple, predictable future or one that is wildly unstable. The simplest model, the one that uses Einstein's cosmological constant, says dark energy is a fixed property of space. Like the background hum of an old refrigerator, it is always there, never changing, steadily pushing the universe apart at an accelerating rate. But what if that hum could grow louder or softer over billions of years? Many physicists suspect dark energy is not constant at all, but a dynamic force field that permeates space, one that could be slowly strengthening or weakening. They call this idea quintessence, named after the fifth element of ancient philosophy. Think of it this way: if the cosmological constant is like a never-dying battery providing a fixed push, quintessence is more like a spring that can be stretched or compressed, its tension changing over cosmic time. A weakening quintessence field could one day fade away, allowing gravity to regain control. A strengthening one could accelerate the expansion so violently it would lead to a catastrophic end for the cosmos. We are trying to measure the heartbeat of the universe across 14 billion years, listening for the faintest change in its rhythm. To do this, astronomers are building the most precise maps of cosmic history ever conceived. Instruments like the upcoming Nancy Grace Roman Space Telescope are designed to peer back across eons, observing millions of distant galaxies and supernovae. Its mission is to trace how the expansion rate has changed with exquisite detail, looking for any subtle deviation from the prediction of a constant dark energy. It will be like watching a movie of the universe's growth played in reverse, frame by frame, searching for a telltale wobble that reveals a dynamic force at work. The data will chart a history of push and pull, a graph of the universe's acceleration. A perfectly straight line on that graph means dark energy is constant, a simple cosmological constant. A curve, however slight, would be a revolution. It would mean the dominant force in the cosmos is alive, changing, and far more complex than we ever imagined. The fate of everything hinges on the shape of that line. This uncertainty about dark energy's nature makes the future of the universe a terrifying gamble. The ultimate fate of everything we see, every galaxy, every planet, every atom, depends entirely on which cosmic force wins the final tug of war. Scientists have outlined several possible endings, each more dramatic than the last, and we are currently gathering evidence to see which path we are on. The first and most likely scenario, based on our current best data, is called the Big Freeze or heat death. In this future, dark energy remains a constant, gentle pressure. The expansion continues to accelerate, but at a steady, unrelenting pace. Over trillions of years, galaxies beyond our own local group will fade from view, their light stretched too far to ever reach us. Stars will burn out one by one until the last embers in the universe go dark. Black holes will slowly evaporate over unimaginable timescales. Eventually, the cosmos becomes a vast, cold, and nearly empty void. The temperature everywhere approaches absolute zero. It is a quiet, desolate end where the universe dies not with a bang but with an endless, frozen whisper. But what if dark energy is not constant? What if it is quintessence and it grows stronger over time? This leads to the most violent possibility, the Big Rip. Imagine the repulsive force of dark energy increasing without limit. First, it would overcome the gravitational glue holding galaxy clusters together. Then it would rip apart individual galaxies. As the force grows stronger still, it would tear stars from their solar systems. In the final moments, minutes before the end, the stretching force would become so powerful it would overcome the forces holding atoms together. Every molecule, every nucleus, every fundamental particle would be violently shredded apart. The fabric of spacetime itself would be torn asunder. the universe would end in a catastrophic, instantaneous flash of disintegration. There is a third, more nostalgic ending, the Big Crunch. This is the classic cosmic reversal. If dark energy were to weaken and fade away, or if there is far more matter in the universe than we think, gravity could finally win. The expansion would slow, halt, and then reverse. Every galaxy would begin rushing back toward every other. The universe would start to collapse in on itself. Temperatures and densities would soar as all matter and energy are compressed into an inferno. The cosmos would end in a fiery mirror of its birth, potentially recycling itself into a new Big Bang. These are not just science fiction stories, they are the direct physical consequences written into the equations of gravity and expansion. Our job now is to be cosmic detectives, reading the clues to see which future is being written. Every measurement of distant supernova, every map of galaxy clusters, every study of the cosmic microwave background is a piece of evidence. We are looking for the slightest hint that dark energy is changing. Is the acceleration getting faster, pointing toward a big rip? Is it steady, dooming us to a big freeze, or could it, against all odds, be slowing? The stakes could not be higher, for the answer tells us not just how the universe ends, but what it truly is made of. The fate of the universe depends on a single critical number. How fast is it expanding right now? This speed is captured in a value called the Hubble constant, named for Edwin Hubble, the astronomer who first discovered the cosmic expansion. It tells us how many kilometers per second a galaxy is moving away from us for every megaparsec of distance. Think of it as the universe's current rate of growth, a single digit that should be consistent no matter how we measure it. Yet here we are, facing a crisis. Two of the most precise methods science has ever devised are giving us two different answers, and the gap between them is only growing wider. On one side, we have a measurement from the dawn of time. The cosmic microwave background is the faint afterglow of the Big Bang, a snapshot of the infant universe when it was only 380,000 years old. By studying the tiny temperature fluctuations in this ancient light with satellites like Planck, we can work backwards through our models of cosmic evolution to predict what the expansion rate should be today. This method gives us a Hubble constant of about 67 kilometers per second per megaparsec. It is a prediction from the baby picture of the cosmos. On the other side, we look at the local, modern universe. Astronomers use cosmic lighthouses called Cepheid variable stars. These stars pulsate with a regularity that is directly tied to their true brightness. By measuring their pulse rate and how dim they appear from Earth, we can calculate their distance with incredible accuracy. We then look at Type Ia supernova in the same galaxies, which are even brighter standard candles. By observing how fast these galaxies are moving away from us and knowing their precise distances, we get a direct measurement of the current expansion rate. This local measurement consistently gives a higher number, around 73 kilometers per second per megaparsec. The difference seems small, just a few units, but in the precise world of cosmology, it is a chasm. These are not crude measurements with large error bars. Both methods have been refined over decades and their uncertainties have shrunk, yet the answers stubbornly refuse to converge. This is the Hubble tension, and it is more than a minor discrepancy. It suggests that something is fundamentally wrong. Either our measurements of the local universe contain a hidden, systematic error we cannot find, or our understanding of the early universe is incomplete. Perhaps the physics that govern the cosmos in its first moments is not what we have written in our textbooks. This tension could be the first crack revealing entirely new particles, forces, or properties of dark energy that our models do not account for. We are forced to ask, is one of our most trusted cosmic rulers broken, or are we reading the map of the universe incorrectly? The answer will rewrite cosmology. The Hubble tension is a discordant note in our symphony of the cosmos, and fixing it may require rewriting the music itself. If our measurements are correct, then the standard model of cosmology, our best and most successful story of the universe, is missing a crucial verse. Scientists are now exploring radical ideas, new physics that could tweak the early universe just enough to make both the ancient and modern expansion rates agree. One compelling proposal is called early dark energy. We know dark energy dominates today, but what if a small amount of this repulsive force also existed in the universe's first moments? Picture the early cosmos as a pot of water coming to a boil. The standard model says it heated up smoothly, but early dark energy would be like a sudden, extra burst of heat right before the boiling point, a brief surge that changes how the bubbles form. In cosmic terms, this fleeting burst would have altered how sound waves traveled through the primordial plasma, subtly changing the patterns we see in the cosmic microwave background. This adjustment could lower the predicted expansion rate from the early universe, bringing it closer to the higher value we see today. It is a tiny tweak with enormous consequences, suggesting dark energy is not just a modern phenomenon but an actor that played a brief, critical role in the opening act. Another possibility lies in the ghostly particles known as neutrinos. The standard model treats them as almost massless particles that stream freely through the universe. But what if some neutrinos were sterile, meaning they interact only through gravity and not the other fundamental forces? Or what if their masses are different than we assume? These exotic neutrinos would have carried away extra energy in the early universe, again altering its development and the resulting prediction for today's expansion. It is like trying to balance a scale where we thought we knew the weight of every object, only to discover one of the weights is made of a mysterious, lighter material. Even gravity itself is under scrutiny. Einstein's theory of general relativity has passed every test for over a century, but the Hubble tension asks if it might need modification on the largest scales. Could gravity behave slightly differently across cosmic distances or in the universe's extreme youth? Some theories propose extra dimensions or new fields that weaken gravity's grip in the early cosmos, allowing it to expand faster initially, which would then align with the faster rate we measure locally. Each of these ideas is an attempt to tune the instrument of the early universe. We have a beautiful melody from the cosmic microwave background and a clear, strong note from the local supernova, but they are out of key. The question is not which note is wrong, but whether our entire instrument, our model of physics, is slightly out of tune. Finding the right adjustment could reveal a universe far richer and stranger than we ever imagined. This tuning of the cosmos leads us to a profound and deeply strange question about the stage on which this entire drama plays out. What is the actual shape of the universe? We instinctively picture it as an endless, three-dimensional void, a flat and infinite expanse. But the equations of general relativity tell us space itself can be curved by the matter and energy within it, meaning the universe as a whole could have a shape. There are only three possibilities, and the fate of everything is written in its geometry. The first possibility is a closed universe shaped like a four-dimensional sphere. In this geometry, if you could travel in a perfectly straight line for long enough, you would eventually loop back to your starting point, just as a ship sailing across the ocean can circumnavigate the Earth. This shape corresponds to a universe where the density of matter and energy is so high that its own gravity will eventually halt and reverse the expansion, leading to a big crunch. It is a finite cosmos without an edge. The second is an open universe curved like a saddle or a Pringle chip. In this shape, parallel lines would forever diverge. Space is curved outward and the universe is infinite. Here, the density is too low for gravity to ever overcome the expansion, dooming it to expand and cool forever in a big freeze. It is an endless hyperbolic landscape. The third and most perplexing is a flat universe. This is the precise knife-edge balance between the closed and open geometries. In a flat universe, parallel lines remain parallel forever. and the rules of classic geometry we learned in school hold true on the largest scales. This geometry implies the expansion will slow asymptotically but never reverse, also leading to a cold end, but it carries a staggering implication. A flat universe is almost certainly infinite. For decades, this was pure theory. Then, we learned to read the universe's baby picture with incredible precision. By studying the subtle patterns in the cosmic microwave background, specifically the size of the hot and cold spots, we can measure the geometry of space. The data from missions like WMAP and Planck delivered a stunningly clear answer. The universe appears to be flat too, within a razor-thin margin of error. This is a monumental discovery. It tells us the total density of matter and energy in the cosmos is exactly at the critical value needed to achieve this flat geometry, a perfect balance that seems too precise to be an accident. But this answer opens a philosophical abyss. A flat universe is likely an infinite universe. If space goes on forever, then every possible configuration of matter must repeat. Somewhere out there, in the vastness beyond our cosmic horizon, there is an identical copy of you, reading an identical copy of this script on an identical Earth. There are infinite variations, worlds where every choice you did not make is reality. This is not science fiction, but a direct consequence of infinity and a finite number of quantum states. The concept is both exhilarating and deeply unsettling. It means that all of our history, every triumph and tragedy, is not unique but a single thread in an infinite tapestry. The universe is not just expanding, its very shape suggests it contains everything that is possible, rendering it fundamentally limitless and, in a way, profoundly lonely. If the stage is infinite, what does that say about the play? An infinite universe is not just a bigger stage, it is a fundamentally different kind of reality. We have measured the geometry and found it flat, but that measurement is like determining the curvature of the ocean from the deck of a single ship. We can only see so far. The ultimate boundary of the cosmos, if it even has one, lies far beyond our observational horizon. That horizon is the limit set by the speed of light and the age of the universe. In the roughly 14 billion years since the Big Bang, light has had only that much time to travel. We can therefore only observe a spherical volume of space 14 billion light-years in radius. Everything beyond that is invisible to us, not because it is not there, but because its light has not had time to reach us yet. So when we say the universe appears flat and infinite, we are making a profound extrapolation. We are taking the geometry we measure inside our tiny, observable bubble and declaring it must apply forever. It is a staggering leap of faith based on the simplest interpretation of our data. But if that leap is correct, the consequences unravel everything we assume about our place in existence. In an infinite, flat universe, there is only a finite number of ways to arrange the fundamental particles in any given volume of space. Think of it like a cosmic chessboard that goes on forever. There are a limited number of possible chess games, so on an infinite board, every possible game will be played not just once, but an infinite number of times. Translate that to the cosmos. With infinite space and a finite set of quantum rules, every possible configuration of matter must repeat. Somewhere, at a distance so vast it is forever beyond our reach, there is a galaxy identical to the Milky Way. In that galaxy, there is a solar system with a planet identical to Earth. On that planet, there is a person identical to you reading these same words. There are also worlds where your life is slightly different, where you made a different choice this morning, and worlds that are utterly alien. Infinity guarantees it all. This idea, known as the cosmological principle taken to its extreme, turns the universe into a vast library containing every story that can possibly be written. It means nothing is unique. Every masterpiece, every tragedy, every moment of joy or despair exists in countless copies across the endless dark. It is a concept that can evoke awe or a profound sense of cosmic loneliness. Our entire history, the sum of human achievement and suffering, becomes a single paragraph in an encyclopedia with infinite volumes. This also places a hard limit on knowledge. No signal, no message, no evidence from these duplicate realms can ever reach us. They are forever outside our causal bubble, racing away from us faster than light can bridge the gap. We are isolated in our pocket of reality, forever wondering about the copies of ourselves we can never meet. The universe may be infinite, but our view of it is, and always will be, tragically finite. This profound isolation forces us to rewind the cosmic film, back to the very beginning, to understand how our observable bubble came to be so uniform and so flat. The answer lies in a theory so dramatic it reshapes our first moments. A fraction of a second after the Big Bang, the universe underwent a growth spurt of unimaginable violence. Scientists call this period cosmic inflation. For a sliver of time so brief it defies comprehension, perhaps from 10 to the power of -36 seconds to 10 to the power of -32 seconds, the cosmos did not just expand, it exploded in size. It swelled by a factor of at least 10 to the power of 26. To grasp that scale, picture a single atom suddenly inflating to become larger than our entire observable universe today. This exponential burst of expansion did more than just make space big. It ironed out the cosmos, solving two of the greatest puzzles in cosmology. The first is the horizon problem. Look at the cosmic microwave background in opposite directions in the sky. Those two patches of the ancient universe are so far apart that, in a standard Big Bang model, light could never have traveled between them to equalize their temperature. Yet they are almost exactly the same. It is as if two people on opposite sides of a vast auditorium who have never met or communicated decided to wear identical outfits. How is this possible? Inflation provides the answer. Before inflation, the entire observable universe was a microscopic speck, a region small enough for light to cross and become perfectly uniform. Then inflation stretched that tiny, smooth region to cosmic proportions, preserving its uniformity across the vast distances we see today. The second puzzle is the flatness problem. Why is the geometry of the universe so perfectly balanced on the knife edge of flatness? Any slight curvature in the infant universe would have been magnified by billions of years of expansion. For the universe to be as flat as we measure it now, its initial conditions had to be fine-tuned to an absurd degree of precision, like balancing a pencil on its tip for 14 billion years. Inflation solves this by acting like a cosmic iron. No matter what shape the universe started with, inflating it by such an enormous factor would have stretched it flat, just as blowing up a balloon makes any small patch on its surface appear flat. This elegant theory is a cornerstone of modern cosmology, but it raises monumental new mysteries of its own. What powered this incredible burst? The leading idea involves a strange energy field called the inflaton. As this field decayed from a high energy state, it released a colossal repulsive force that drove inflation, eventually settling down and dumping its energy into creating the hot soup of particles of the classic Big Bang. But we have no idea what the inflaton field actually is, or what triggered its sudden decay to end the inflationary epoch. The search for proof hinges on finding a specific fingerprint inflation would have left on the cosmos' primordial gravitational waves. These are ripples in spacetime itself, generated by the violent quantum fluctuations of the inflaton field as space stretched. They would have imprinted a unique swirling pattern called B-mode polarization on the cosmic microwave background. Detecting that pattern would be a direct window into the universe's first instant. Experiments have hunted for it, but so far the signal remains elusive, hidden beneath cosmic dust and other interference. The trigger for inflation and its abrupt end are locked in that first trillionth of a second, a realm where our laws of physics break down. We are left with a breathtaking story, one that explains so much about the cosmos we see, yet is built upon a force and a mechanism we have never directly observed. If inflation truly happened, it may have created far more than just our universe. The same mechanism that smoothed and stretched our cosmic neighborhood could be spawning an endless sea of other realities, each with its own unique laws of physics. This is the staggering idea of the multiverse, and it emerges naturally from a leading version of the inflationary theory called eternal inflation. Picture the inflattened field, that strange energy that powered the universe's explosive growth, as a vast mountainous landscape. At the peak of the highest mountain, the field is brimming with energy, creating a repulsive force so strong it causes space to inflate at an exponential rate. Now imagine this mountain is not solid rock, but more like a frothing, bubbling liquid. Quantum fluctuations cause parts of the field to randomly tumble down into valleys below. In each valley, the inflattened field has a lower energy. When a region of space tumbles into a valley, inflation stops for that region. The enormous energy of the inflattened field is released in a fiery burst, creating the hot soup of a big bang and birthing a new bubble universe like ours. But here is the crucial part. The mountain peak is still actively inflating, stretching space faster than the bubbles can form. So while one region drops out to become a bubble, the space around it is still expanding wildly. This process never stops. New bubbles are constantly forming in the eternally inflating background, each one isolated from the others, each one a separate universe within a greater multiverse. Think of a pot of boiling water on a stove that never runs out of heat. Bubbles rise to the surface and pop, but new ones are always forming beneath them. In eternal inflation, the pot is the inflattened field, and each bubble is an entire cosmos forever being created. This leads to a breathtaking and almost unsettling possibility. The valleys our inflattened field could tumble into are not all the same. Some valleys are deep, some are shallow. Each represents a different stable state, a different set of physical constants. When a bubble universe forms in a particular valley, it inherits the laws of physics tied to that energy state. In one bubble, the strength of gravity might be 10 times stronger. In another, electromagnetism might be too weak to hold atoms together. In most of these bubbles, the conditions would be so alien that stars, planets, and life as we know it could never form. Our universe, with its precise, life-permitting constants, would be just one rare bubble in a vast cosmic froth, a lucky roll of the dice in an infinite casino. This is not pure philosophy, but a mathematical consequence of applying quantum mechanics to the inflationary model. It pushes cosmology to its absolute limit, transforming our universe from a singular event into a single page in an infinite book of possible realities. The multiverse may be the ultimate frontier, a realm forever beyond our observation, where the very rules of existence are as variable as the weather. The multiverse paints a cosmos of infinite possibilities, but our own universe is governed by a different kind of shadow. To understand how the grand expansion plays out, we must first confront the cosmic scaffolding that holds everything together. This brings us to the second great enigma of the cosmos, dark matter. While dark energy pushes the universe apart, dark matter is the hidden glue that pulls it into shape, and its mysterious nature is deeply entwined with the story of expansion. The evidence for dark matter is overwhelming, yet it comes from what we cannot see. The first major clue came from the way galaxies spin. Stars on the outer edges of spiral galaxies orbit the galactic center, just like planets orbit a star. According to the laws of gravity, these distant stars should be moving much slower because the visible mass of the galaxy, all the stars and gas we can see, is concentrated in the bright central bulge. But observations tell a different story. Stars on the outskirts orbit just as fast as those near the center. The only explanation is that each galaxy is embedded in a vast, invisible halo of matter, a halo that extends far beyond the luminous edge of the galaxy. This unseen mass provides the extra gravitational pull to keep those fast-moving stars from flying off into intergalactic space. It is as if you watched children on a merry-go-round, and those on the very outside were spinning just as fast as those near the center, implying there must be some hidden, massive structure holding the whole ride together. The second, even more dramatic proof comes from a phenomenon predicted by Einstein: gravitational lensing. Massive objects warp the fabric of space-time, bending the path of light that passes near them. When we look at massive galaxy clusters, we see distant galaxies behind them stretched and distorted into faint arcs and rings, like looking through a cosmic magnifying glass made of gravity. By measuring how much the light is bent, we can calculate the total mass of the cluster doing the bending. The result is always the same. The mass required to create that lensing effect is many times greater than the mass of all the visible stars and hot gas combined. The majority of the cluster's gravity comes from something invisible, something that permeates the entire cluster in a giant cloud. This dark matter forms the skeleton of the cosmos, the framework upon which galaxies and clusters are built. So what is this mysterious substance? We know it is not made of atoms, not protons or neutrons or electrons. It does not emit, absorb, or reflect light, hence it is dark. It interacts with ordinary matter almost exclusively through gravity. The leading candidate for decades has been a hypothetical particle called a WIMP, a weakly interacting massive particle. As the name suggests, WIMP would be heavy particles that rarely bump into ordinary matter, passing right through our planet as if it were not there. Physicists have built exquisitely sensitive detectors deep underground, shielded from cosmic rays, hoping to catch the faintest vibration from a WIMP collision. So far, the detectors have remained silent. Another compelling candidate is the action, a particle conceived to solve a different puzzle in particle physics. Actions would be incredibly light, almost ghostly, and could stream through the universe in vast numbers. Experiments are now using powerful magnetic fields to try and convert these elusive actions into detectable photons. The hunt is urgent because dark matter is not a side mystery. It is central to modeling the universe's expansion accurately. The gravitational pull of all matter, both dark and visible, acts as a brake on the expansion. To calculate how fast the universe should be expanding today, we need to know how much matter there was in the past to slow it down. If we are wrong about the amount or the behavior of dark matter, our entire cosmic timeline is off. Furthermore, the way dark matter clumps together under gravity seeds the formation of the first galaxies and clusters. That early structure formation sets the initial conditions that dark energy later works against as it accelerates the expansion. We cannot understand the push without fully understanding the pull. Dark matter is the silent partner in this cosmic dance, its steps dictating the rhythm long before dark energy took the lead. Without knowing its true identity, we are trying to read a history book with half the pages written in invisible ink. The silent partner of dark matter sculpts the cosmos, but at the heart of almost every galaxy sits a different kind of monster, one that actively roars. Supermassive black holes, with masses millions or even billions of times that of our Sun, are not passive sinkholes. They are dynamic engines, and the energy they unleash may subtly steer the very expansion they inhabit. To understand their potential influence, we must first see them in action. Most of the time, a supermassive black hole is quiet, like a sleeping beast. But when a torrent of gas and dust from the surrounding galaxy spirals into its accretion disk, the beast awakens. Friction heats this orbiting material to millions of degrees, causing it to glow brilliantly across the electromagnetic spectrum. In this active state, the galaxy's core becomes a quasar, outshining every star in its host galaxy combined. But the black hole's influence does not stop with light. Intense magnetic fields can channel some of the infalling material into focused beams, launching jets of plasma at nearly the speed of light that can stretch for hundreds of thousands of light years. These jets are cosmic blowtorches punching through the galaxy and into intergalactic space. So how does this violent activity connect to the grand expansion of the universe? The link is indirect but profound through a process called feedback. When those powerful quasar winds and relativistic jets slam into the surrounding galactic gas, they do two contradictory things. First, they can shock and compress clouds of gas, triggering intense bursts of new star formation. But more often and more significantly, they can blast that gas completely out of the galaxy. Think of it as a galactic-scale cleaning event. By heating and ejecting the raw fuel for making new stars, the black hole effectively puts a limit on the growth of its own galaxy. This is a self-regulating mechanism. A galaxy cannot grow endlessly if its central engine keeps emptying its gas tank. This stellar feedback has a cascading effect on the large-scale structure of the cosmos. The gas blown out into the space between galaxies becomes part of the intergalactic medium, altering its temperature and density. Since the gravitational pull of matter is what slows the cosmic expansion, anything that changes how matter is distributed can, in theory, tweak the expansion's history. If supermassive black holes efficiently suppress star formation in massive galaxies, they change how many bright stars exist over cosmic time, which in turn affects how we measure distances and expansion rates using those stars as beacons. Furthermore, the colossal energy these black holes inject into their surroundings might even counteract gravity on local scales, making it slightly harder for galaxy clusters to hold onto their gas. While their direct gravitational influence is limited to their immediate vicinity, their energetic output ripples through the cosmic web. They are not driving the expansion like dark energy, but they are powerful actors on the stage, shaping the environment in which the expansion plays out. Their growth through mergers and accretion is a parallel history to the expansion of space itself, a reminder that the universe's large-scale story is woven from countless dramatic local events. The violent energy of black holes shapes galaxies, but the true architects of cosmic structure may be far more elusive. To understand the universe's expansion, we must account for every form of energy that has ever existed, including the most ghostly particles known to physics, neutrinos. Trillions of these subatomic phantoms are streaming through your body every second, utterly unnoticed. Born in the nuclear furnaces of stars and in the cataclysmic violence of the Big Bang, they interact with matter so rarely they can pass through light years of lead without a single collision. In the universe's first few moments, this indifference was their defining feature. For hundreds of thousands of years after the Big Bang, the cosmos was a dense, opaque soup of particles. Light photons were trapped, constantly bouncing off electrons, but neutrinos, once formed, simply left. They stopped interacting with other matter when the universe was just 1 second old and have been traveling freely ever since. This early exit makes them a unique fossil, a pristine messenger from the universe's first heartbeat. Back then, they were relativistic, moving at almost the speed of light. Their frenetic motion created a subtle pressure that smoothed out the densest clumps of matter, slightly delaying the moment when gravity could begin pulling galaxies together. Think of neutrinos as a cosmic wind blowing through wet cement. Their constant movement prevented the mix from settling as quickly as it otherwise would have, subtly altering the final texture of the cosmic structure we see today. This delay is a critical parameter in our models. If we get the neutrino story wrong, our predictions for when the first stars ignited could be off by millions of years. Today, these particles are still here, but they have slowed down. As the universe expanded and cooled, neutrinos lost most of their blistering speed. We now know they have a tiny but non-zero mass. This mass, however minuscule, means they contribute to the universe's total mass-energy budget. While one neutrino is insignificantly light, their numbers are astronomically vast. There are roughly 1 billion neutrinos for every proton in the universe. Collectively, their gravitational influence adds up, acting as a small but meaningful drag on the expansion. They are a diffuse, pervasive component of the cosmic fog we must include in our accounting. The problem is, we do not know their exact masses. We have only measured the differences between the masses of the three known types or flavors of neutrinos. We know they have mass, but we do not know the absolute scale. Are they as light as a millionth of an electron's mass or 1,000 times heavier? This uncertainty leaves a hole in our cosmic ledger. Their gravitational pull in the past affects how fast we think the universe should be expanding now. If neutrinos are heavier than our best guesses, they would have acted as a stronger break in the early universe, which could help explain the tension between the different measurements of the expansion rate. This leads to an even more speculative idea: sterile neutrinos. These are hypothetical particles that would not interact through any of the known forces except gravity. They would be even more ghostly than their ordinary cousins. If they exist, sterile neutrinos could have been a major component of dark matter in the early universe, radically altering the timeline of structure formation. They might have helped clump matter together sooner, or perhaps smoothed it out further. Their potential influence is so profound that including them in models can significantly shift the predicted expansion history, offering another possible solution to the Hubble tension. We are left chasing shadows to balance the books of the cosmos. The exact mass of the neutrino is not just a particle physics puzzle, it is a missing variable in the grand equation of the universe's growth. Until we pin it down, a piece of our cosmic story remains written in invisible ink, its words felt only through gravity's faintest touch. The universe runs on a set of rules so precise we can use them to predict the behavior of galaxies billions of light years away. But what if the rulebook itself is changing? This leads us to one of the most radical questions in all of science. Are the laws of physics constant across space and time? Could the very numbers that define reality, the fundamental constants, be slowly drifting? The implications are staggering because a change in one of these constants could mimic dark energy or even render it unnecessary. The fine structure constant is one such number. It governs the strength of the electromagnetic force, dictating how atoms hold together and how light interacts with matter. Its value is approximately 1/137. If this number were even slightly different, the chemistry of life would be impossible, stars could not burn, and the universe would be unrecognizable. For decades, we assumed it was fixed, a timeless pillar of reality. But what if it is not? Astronomers have devised a brilliant experiment to test this. They look at the light from incredibly distant quasars, the luminous cores of ancient galaxies. As this light travels for billions of years across the expanding universe, it passes through clouds of interstellar gas. Atoms in these clouds absorb specific wavelengths of the quasar's light, creating dark lines in the spectrum like a barcode. The position of these absorption lines depends intimately on the value of the fine structure constant. By comparing the barcodes from ancient, distant gas clouds to those produced in laboratories on Earth today, we can check if the constant has changed. Some teams have reported tantalizing, controversial evidence of a very slight variation in the fine structure constant over billions of years. The signal is faint and fiercely debated, but if true, it would mean the fabric of reality is not static. Even gravity's strength, defined by Newton's gravitational constant, big G, is under scrutiny. A changing big G would mean gravity itself was stronger or weaker in the past, which would dramatically alter the expansion history of the cosmos. A stronger gravity in the early universe would have slowed the initial expansion more fiercely, which could help reconcile the conflicting measurements of today's expansion rate. To test this, scientists look not only to the stars but to the ground beneath our feet. They examine the nuclear reactions in a 2-billion-year-old natural nuclear reactor found in Oklo, Gabon. The way these ancient fission products decayed is exquisitely sensitive to the values of several fundamental constants. Analyzing this prehistoric reactor is like finding a cosmic stopwatch buried in the Earth, one that ticks at a rate set by the laws of physics 2 billion years ago. So far, the OCLO data suggests the constants have been stable, but the search continues with ever greater precision. If a drift in constants were proven, it would upend everything. A changing fine structure constant could mean the strength of the vacuum of space itself is evolving. This evolving vacuum energy could act exactly like a dynamic form of dark energy, a quintessence field that drives acceleration. In this scenario, dark energy is not a new substance, but a symptom of our most fundamental laws slowly unraveling. The universe expands not because of a mysterious anti-gravity force, but because the rules of the game are subtly, inexorably shifting. We are left questioning the bedrock of science itself. Is our cosmos governed by eternal, immutable laws, or are we living in a universe whose very rules are part of its unfolding story, a story still being written? If the laws themselves can change, then the very stage they act upon must also be questioned. Space and time are not just a passive backdrop for the cosmic drama. They are the lead actors, a dynamic fabric woven together into a single entity called space-time. But what is this fabric made of? Is it perfectly smooth and continuous, like a boundless, unblemished sheet of silk? Or is it fundamentally grainy and foamy when viewed at the smallest imaginable scales? The answer could determine whether our theories of the very big and the very small can ever be reconciled, and it may leave a subtle imprint on the expansion of the universe itself. Our best theory of the large-scale cosmos, Einstein's general relativity, treats space-time as a smooth, continuous landscape that can curve and warp under the influence of mass and energy. It is a breathtakingly successful description of gravity, predicting black holes' gravitational waves and the expanding universe with incredible precision. But when we try to merge this theory with quantum mechanics, the rules that govern atoms and particles, everything breaks down. Quantum mechanics tells us that energy comes in tiny, discrete packets called quanta. Light is made of photons, matter is made of particles, so why should the fabric of space-time itself be any different? Perhaps at the deepest level, space and time are also pixelated. This idea leads to theories like loop quantum gravity, which proposes that space itself is woven from a network of incredibly tiny, one-dimensional loops. These loops at the Planck scale, a distance a billion times smaller than an atomic nucleus, connect to form a fabric that is not smooth but a dynamic, ever-changing mesh. In this view, there is a smallest possible unit of space, a quantum of volume, just as there is a smallest possible unit of light. Time, too, may be granular, ticking forward in discrete, indivisible moments rather than flowing as a continuous river. This quantum foam, as it is often called, would be a seething, turbulent sea of virtual particles and fluctuating geometry at the tiniest scales. But how could this microscopic froth possibly affect something as vast as the expansion of the entire cosmos? The link is subtle but profound. If space-time has a granular structure, then over immense distances, the cumulative effect of these tiny irregularities could become measurable. Think of it like walking across a perfectly smooth floor versus walking across a cobblestone street. On the scale of a single step, the cobblestones are a minor texture. But if you had to walk 1,000 miles, the constant, tiny variations would add up, potentially slowing you down or altering your path in a predictable way. Similarly, light traveling across billions of light years of a foamy space-time might be slightly scattered or delayed. Some theories suggest that higher energy photons, like gamma rays, might interact with this quantum graininess more than lower energy light, causing them to arrive at our telescopes at slightly different times after a long journey. Astronomers have looked for this effect in the light from distant gamma-ray bursts and other cosmic explosions. So far, no definitive signal has been found, meaning if foam exists, its grains are unimaginably fine. Yet the quest continues because the nature of space-time is the ultimate foundation. If it is granular, then our smooth equations of expansion are an approximation, a large-scale average of a frenzied quantum reality. The acceleration driven by dark energy might not be a force acting upon space, but an emergent property of space-time's quantum structure rewriting its own geometry from the bottom up. We are left peering into the abyss of the infinitesimally small, searching for clues that might explain the behavior of the entire visible universe. The quantum foam of space-time hints at a reality beneath our smooth equations, but to understand the expansion, we must confront the event that started it all. What caused the Big Bang? This is the ultimate origin question, the moment where all our confident physics dissolves into a blinding flash of unknowing. Our story of the expanding cosmos traces back to a hot, dense, singular point, but the question of what came before that point, or what sparked its existence, pushes us to the very edge of human comprehension. The classical Big Bang model describes the expansion from an initial state of infinite density and temperature, a singularity. At that point, the equations of general relativity break down completely. They cannot describe the conditions, let alone what preceded them. It is like using a map of a city to navigate the precise moment a volcano erupts. The tools are simply not built for the task. To peer behind that veil, we must turn to speculative ideas that blend cosmology with the frontiers of theoretical physics. One profound possibility is that the universe emerged from a quantum fluctuation in a state of pure nothingness. In this view, nothing is not an empty void, but the complete absence of space, time, and matter. Yet, according to quantum mechanics, even such a true nothing is unstable. Virtual particles constantly blink in and out of existence in our universe, borrowing energy from the vacuum for fleeting moments. Could the entire cosmos be the ultimate quantum fluctuation, a bubble of space-time that simply popped into being? If so, the total energy of the universe might be precisely zero, with the positive energy of all matter and radiation perfectly balanced by the negative gravitational energy of space itself. Our entire existence would be a grand and persistent example of something from nothing, a free lunch written into the laws of quantum reality. A less abstract idea suggests there was no true beginning at all. Perhaps our Big Bang was not a birth from nothing, but a rebound from a previous death. This is the cyclic or bouncing universe model. In one version, the universe undergoes endless cycles of expansion and contraction. It expands until dark energy dissipates and gravity pulls everything back together in a big crunch. Instead of collapsing to a point of infinite density, quantum effects at the smallest scales create a repulsive force, causing the universe to bounce back outward in a new Big Bang. Each cycle erases the specific details of the last, but the cosmos itself is eternal, breathing in and out across eons. Our expanding universe is just one heartbeat in an infinite series. String theory, a candidate for a theory of everything, offers an even more exotic origin story, the brane collision. In this model, our three-dimensional universe is a membrane or brane floating in a higher dimensional space. Other branes may exist parallel to ours. If two such branes were to collide in the extra dimensions, the immense energy of that impact could have ignited the hot, dense state we call the Big Bang. Our universe's expansion is the aftermath of that cosmic collision, and the cycles could continue as branes oscillate and collide again in the future. Each of these ideas is a narrative we stretch over the abyss of our ignorance. They are compelling stories that attempt to answer the unanswerable, yet they all share a common, humbling truth. At the moment of the Big Bang, our concepts of before and after, of cause and effect, may cease to have any meaning. Time itself may have begun with that event. Asking what came before the Big Bang could be as nonsensical as asking what is north of the North Pole. We are trying to use language and logic forged within the universe to describe its own origin, a task that may be inherently impossible. This is the profound limit of our understanding, a horizon beyond which our science, for now, cannot see. Our cosmic horizon is a hard limit, not a wall. We can only see the light that has had time to reach us in the roughly 14 billion years since the Big Bang. This defines a sphere around us, the observable universe, with a radius of about 46 billion light-years. That staggering distance accounts for the expansion of space itself, stretching the light's journey far beyond a simple 14 billion light-years. Everything within that colossal bubble is our entire reality, every galaxy, every quasar, every photon we will ever detect. But the universe itself is almost certainly larger, perhaps infinitely so. So what lies beyond that boundary, in the regions whose light has not yet, and may never, reach us? The simplest answer, guided by the cosmological principle, is that it is more of the same. More galaxies, more stars, more cosmic voids, arranged in the same vast web of structure we see around us. If the universe is indeed flat and infinite, then beyond our horizon stretches an endless repetition of the cosmic tapestry, with every possible variation played out across an unfathomable expanse. There could be superclusters of galaxies dwarfing anything in our view, or immense voids so vast they make our local emptiness seem crowded. But the principle of uniformity is an assumption, one we cannot test. It is entirely possible that the conditions beyond our horizon are radically different. Perhaps the density of matter varies wildly on scales larger than we can see. There could be domains where the strength of gravity or other fundamental constants are different, regions born from a slightly different outcome in the chaotic first moments of inflation. Some theories even suggest our entire observable universe is just one bubble in a frothing multiverse, and beyond our horizon lies a completely different bubble universe with its own distinct laws of physics, forever separated from us by an eternally expanding sea of inflating space. This leads to a profound and humbling philosophical reality. We are fundamentally trapped within our observable bubble. No signal, no information, no evidence from those external realms can ever reach us because the space between us is expanding faster than light can traverse it. They are causally disconnected from our existence. We can theorize, we can extrapolate, but we can never know. The universe may be infinite, but our knowledge of it is permanently, tragically finite. We are like sailors on a vast, foggy ocean. We can see a certain distance in every direction, a circle of visibility defined by the light. We map the waves and islands within that circle with great care, and we assume the ocean continues in much the same way beyond. But for all we know, just past the edge of our sight, the water ends in a waterfall into an abyss, or transforms into a sea of crystal or fire. We will never sail there, and no message from those distant waters will ever drift into our view. This is the ultimate limit of empirical science. It forces us to confront the difference between the universe and our universe. One may be everything that exists, the other is merely everything we can ever hope to see or measure. The true nature of reality may lie forever in the dark, just beyond the reach of our most powerful telescopes, a permanent mystery written in the geometry of space and time itself. The cosmic microwave background is the most important photograph in history, a snapshot of the infant universe. Yet when we stare into this baby picture, we see unsettling features that should not be there. These are not just minor blemishes, but colossal anomalies that challenge our standard story of a uniform, isotropic cosmos born from inflation. The first and perhaps most famous is the cold spot. In a sea of tiny temperature variations, this is a vast, circular region in the constellation Eridanus that is significantly colder than its surroundings. It is enormous, spanning nearly 1 billion light-years across. At first, astronomers thought it might be a giant cosmic void, an empty region of space so vast that light passing through it would lose energy, creating a cold imprint. Yet surveys have found no corresponding void large enough to explain it. This leaves more exotic possibilities. Could the cold spot be a bruise, a remnant of a collision between our bubble universe and another bubble in the multiverse? Or is it a window into a pre-Big Bang structure, a scar from the chaotic physics of the earliest moments? Then there is the so-called axis of evil. This is not a malevolent force, but a bizarre alignment in the data. The hot and cold spots in the cosmic microwave background are not randomly distributed as inflation predicts. Instead, they show a strange statistical alignment along a particular axis in space, as if the universe has a preferred direction. It is as if you took a fingerprint and found all the ridges lined up in parallel, defying the expectation of total randomness. Furthermore, the two hemispheres of the sky show a puzzling asymmetry. One half of the universe appears to have slightly larger temperature fluctuations than the other. It is like looking at a painted wall where one side has a noticeably rougher texture than the other, suggesting the paint was not applied evenly. Are these just statistical flukes, the universe rolling a very unlikely set of dice? With the exquisite precision of satellites like Planck, the odds of such flukes grow increasingly slim. Each anomaly whispers that our simple, elegant model of inflation might be incomplete. They hint at a cosmos that is not perfectly uniform, one that may have inherited quirks from a more complex birth. Perhaps inflation did not erase all traces of what came before. These strange features could be fossils, the last echoes of a time before our Big Bang, or signatures of a larger multiversal geography we are only beginning to sense. They are ghosts in the machine of creation, and their silent presence reminds us that the universe's first light may still hold secrets we have yet to fully decipher. These ghosts in the cosmic background point to a deeper fracture in our understanding of reality. To truly grasp the universe's first moments, we must confront the greatest unsolved problem in physics, the search for quantum gravity. Our two most successful theories are spectacularly incompatible. General relativity paints the cosmos on a grand canvas, describing gravity as the curvature of smooth, continuous space-time, perfectly explaining the expansion of the universe, black holes, and the Big Bang. Quantum mechanics, in stark contrast, reveals a frenzied, probabilistic world of discrete particles and forces at the smallest scales. Each theory reigns supreme in its own domain, but they utterly fail when forced to meet. At the heart of the Big Bang and at the center of every black hole lies a singularity, a point of infinite density where the smooth fabric of general relativity breaks down. Here, quantum effects must take over, but we have no theory to tell us how. This is the chasm quantum gravity seeks to bridge, and its implications for the universe's expansion are profound. The leading candidate for this unified theory is string theory. It proposes a radical fix that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating strings. Each distinct vibration corresponds to a different particle, like a note on a guitar string producing an electron or a photon. Crucially, one of these vibrational modes is the graviton, the hypothetical quantum particle that would carry the force of gravity. This elegantly brings gravity into the quantum fold, but the mathematics of string theory demands a shocking price: extra dimensions. For the equations to work, the universe must have not just the 3 spatial dimensions we experience, but 6 or 7 more, all curled up into a space so small we cannot perceive them. Think of a garden hose viewed from a distance. It looks like a one-dimensional line, but up close, you see it has a circular, 2-dimensional surface. The extra dimensions of string theory are similarly compactified, hidden from our everyday view. How does this reshape the early universe? String theory provides a natural home for the inflattened field, the engine of cosmic inflation. That field could be a specific configuration of strings and extra dimensions. More dramatically, string theory may eliminate the Big Bang singularity entirely. In some models, our universe could have arisen from the collision of higher dimensional membranes, or from the death and rebirth of a previous cosmos in an endless cycle, with the transition smoothed by quantum string effects. There would be no point of infinite density, no true beginning where physics stops, but rather a bounce or a collision where our familiar expansion emerged from a pre-existing quantum geometry. Another approach, loop quantum gravity, takes a different path. It keeps space-time itself but quantizes it, proposing that space is woven from a network of tiny, discrete loops. This creates a fabric that is not smooth but granular at the Planck scale. In this theory, the Big Bang is replaced by a big bounce. As a previous universe contracted, the increasing density would reach a point where the quantum graininess of space creates a tremendous repulsive force, causing the universe to rebound into the expansion we see today. Both ideas offer a vision of the earliest moments where quantum gravity doesn't just tweak the expansion, it defines it. The violent acceleration of inflation and the birth of the cosmos become natural consequences of a deeper, unified physics. Yet here lies the monumental challenge testing these ideas. The energy scales at which these quantum gravity effects become obvious are a quadrillion times higher than what our most powerful particle colliders can reach. We are trying to hear a whisper in a hurricane. Scientists are therefore forced to be detectives, looking for indirect cosmic fossils. They search for imprints of those extra dimensions or the granularity of space in the cosmic microwave background, perhaps in the pattern of gravitational waves from inflation. They analyze the light from distant gamma-ray bursts for signs that different energy photons were slowed slightly differently by a foamy space-time structure. So far, the evidence remains elusive. The quest for quantum gravity is a leap of faith into the mathematical sublime, a belief that the universe's deepest secrets, from its explosive birth to its ultimate fate, are written in a language we have only begun to decipher. This relentless search for origins forces us to consider a breathtaking possibility. Perhaps the Big Bang was not a unique beginning, but merely one chapter in an eternal story. Do we live in a cyclic universe, a cosmos that breathes in and out across eons, forever dying and being reborn? This ancient idea has found new life in modern physics through two radical models. The first is called conformal cyclic cosmology, proposed by the Nobel laureate Roger Penrose. In this vision, the universe is not a single linear timeline, but a series of disconnected eons. Each eon begins with its own Big Bang and expands forever, driven by dark energy until all matter decays and black holes evaporate. In this distant, empty future, the universe becomes a vast, featureless sea of low-energy photons. With no matter to define scale, space and time lose all meaning. This smooth, cold end state, Penrose suggests, becomes mathematically identical to the hot, smooth beginning of a new Big Bang. The end of one eon seamlessly transforms into the start of the next, in an endless cycle where time itself resets. It is a profound and poetic idea where the heat death of one universe is the womb for the next. The second model is the ekpyrotic scenario, born from string theory. Here, our three-dimensional universe is a membrane floating in a higher dimensional space parallel to another brane. These two branes could periodically collide, with each collision releasing immense energy that we experience as a hot, dense Big Bang. The universes then expand and cool, drifting apart, only to be drawn together again for another collision billions of years later. This creates a cyclic pattern of brane collisions, a cosmic heartbeat in the bulk of extra dimensions. Both models offer a powerful allure. They eliminate the need for a singular, inexplicable beginning. There is no moment of creation from nothing, only an eternal transformation from one state to another. But how could we ever test such a grand idea? The key is to look for scars. If our universe was born from the death of a previous one, might there be traces left behind? Penrose and his colleagues have searched the cosmic microwave background for a specific signature, concentric circular patterns of temperature variation. These circles, they argue, could be imprints of gravitational waves generated by the collisions of supermassive black holes in the previous eon, etched onto the sky as it reset. It is a controversial claim, and most analyzers of the Planck satellite data have not confirmed these patterns. The search for evidence of brane collisions is even more challenging, potentially hidden in the detailed spectrum of primordial gravitational waves, a signal we have yet to detect with certainty. The cyclic universe remains a magnificent speculation, a story that offers cosmic comfort by making our existence part of an infinite rhythm. Yet it also presents a dizzying prospect. If true, everything we know, every galaxy, every star, every life, has happened an infinite number of times before and will happen an infinite number of times again. We are living a moment in an endless loop, a thought that is as awe-inspiring as it is haunting. This strange alignment has a name that sounds more like a cosmic thriller than a scientific paper, the axis of evil. It refers to a bizarre and controversial pattern found in the largest scale fluctuations of the cosmic microwave background. When scientists decompose the CMB's temperature map into its fundamental components, like separating a musical chord into its individual notes, the lowest notes, the largest waves across the sky, show a peculiar coherence. Their hot and cold spots appear aligned along a specific axis, a preferred direction in space that seems to point roughly toward the constellations of Leo and Virgo. This is deeply unsettling. The cosmological principle, a bedrock assumption of modern cosmology, states that the universe is isotropic, meaning it looks the same in every direction when viewed on a large enough scale. There should be no special axis, no cosmic north. The axis of evil, if real, points a finger directly at that principle, suggesting the universe has a spine, a fundamental orientation that should not exist. The immediate reaction from many scientists was profound skepticism. Could this be an artifact, a ghost in the machine? The most prominent suspect is foreground contamination from our own Milky Way. Our galaxy's dust and synchrotron radiation emit microwaves that must be meticulously subtracted from the raw satellite data to reveal the pristine CMB beneath. Perhaps the cleaning process was imperfect, leaving a faint directional smear that mimics an alignment. Teams have analyzed the data from both the WMAP and Planck satellites with ever more sophisticated techniques. And while the foregrounds do contribute to the signal, a stubborn residual alignment persists. Others wonder if it is a statistical fluke. With any complex dataset, you can find strange patterns if you look hard enough. The universe might simply have rolled a very unlikely set of dice, producing a pattern that looks special to us but is in fact random. Yet as measurements improve and the anomaly refuses to vanish, the possibility that it is a real feature of the cosmos grows harder to dismiss. If we take it seriously, the implications are revolutionary. It could mean that inflation, the process that supposedly made the universe uniform, did not erase all traces of its initial conditions. The axis of evil might be a fossil, a relic of a pre-inflationary universe that had structure and directionality. Perhaps our cosmos is not perfectly isotropic because it was born with a slight twist, a primordial rotation or shear imprinted on its fabric. Some have even speculated it could be evidence of a larger multiversal geography, a tug from a neighboring universe or bubble that left a directional imprint on our own. This single, eerie alignment forces us to question the very framework we use to interpret the cosmos. Are we seeing a crack in the foundation or just a trick of the light? The answer lies in future observations, in maps of the CMB with even greater precision and new ways to separate galactic noise from cosmic signal. Until then, the axis of evil remains a haunting question mark in the sky, a whisper that our universe might have a favorite direction after all. The universe's eerie alignment might be a clue pointing beyond our familiar three dimensions. If our reality is embedded within a higher dimensional space, the very rules of gravity and expansion could be rewritten. This is the startling promise of string theory and its vision of a cosmos with extra dimensions. We experience a world of length, width, and height, but theoretical physics suggests there could be 6 or 7 more spatial dimensions curled up into a space so fantastically tiny that they are hidden from our perception. Think of a drinking straw. From a distance, it looks like a simple one-dimensional line, but up close, you see it has a circular second dimension wrapped around its length. Extra dimensions could be similarly compactified, existing at every point in our space but folded away. How could these hidden realms affect the expansion of our universe? The answer lies with gravity. In our standard model, gravity is the weakest of the fundamental forces, a fact that has long puzzled scientists. But in theories with extra dimensions, gravity's apparent weakness is an illusion. It might be a force that is actually strong and vibrant, but it is diluted because it can leak out into the bulk of these higher dimensions. Only a fraction of its strength is felt in our three-dimensional brain, the membrane of our reality. This changes the entire cosmic equation. If gravity's true nature is diluted, then its role in the early universe's expansion history could be different than we calculate. The way it braked the initial explosive growth might have been subtly altered, which could in turn affect our predictions for today's expansion rate, offering a potential solution to the Hubble tension. This idea blossoms into a full-fledged cosmological model called brainworld cosmology. In this picture, our entire three-dimensional universe is a brain floating within a higher dimensional space called the bulk. Other brains might exist parallel to ours, like sheets of paper suspended in a vast room. Dark energy itself could be a ghostly manifestation of our brain's interaction with the bulk or with a neighboring brain. The repulsive force accelerating the cosmos might not be a property of empty space within our brain, but a gravitational push from another universe just millimeters away in an unseen dimension. Imagine 2 sheets of paper lying flat on a table. They don't touch, but if you could perceive a third dimension perpendicular to the table, you could see they are parallel and separate. In a similar way, a parallel brain could be incredibly close in a higher dimension, and its gravitational influence could stretch our space from the outside. This external stretching would look exactly like an internal dark energy to us, trapped as we are on our three-dimensional sheet. The quest to detect these extra dimensions is a hunt for the most subtle of signatures. Scientists are looking for them in particle colliders, hoping to see energy momentarily disappear into a hidden dimension. They are also looking to the cosmos. If gravity behaves differently at extremely small scales or over vast distances due to leakage, it might leave an imprint on the orbits of stars within galaxies or the way galaxy clusters bend light. The search is for a crack in the three-dimensional world we take for granted, a whisper from a larger, more intricate reality where the true story of the universe's expansion is being written. This precise age, 13.8 billion years, is the cornerstone of our cosmic timeline. But like a tower built on shifting sand, its foundation is the expansion history itself. The universe's age is not measured with a simple clock. It is calculated by rewinding the movie of the expansion, seeing how long it would take for all galaxies to rush back together into the hot, dense state of the Big Bang. The speed of that rewind is set by the Hubble constant. A faster expansion rate today means it took less time for the universe to reach its current size, implying a younger cosmos. A slower rate points to a more ancient, more leisurely expansion. This direct link turns the Hubble tension into a crisis of cosmic chronology. If the local measurement of 73 is correct, the universe could be as young as 12.5 billion years. If the early universe prediction of 67 holds, the age stays near 13.8 billion. This is not a trivial gap, it is over 1 billion years of missing history. A younger universe creates an immediate and profound paradox when we look at some of the oldest objects within it. In the Milky Way's halo, there exists a star catalogued as HD 140283, but known more poetically as the Methuselah star. By analyzing its light, astronomers have determined its composition. It contains very little iron, a metal forged only in the hearts of massive stars and scattered by their supernova explosions. The lower the iron content, the older the star, because it formed from pristine gas before many supernovae had polluted the cosmos. The Methuselah star's iron level is astonishingly low, placing its estimated age at around 14.5 billion years, plus or minus 800 million. That is older than the calculated age of the universe itself. It is as if we found a photograph dated before the invention of the camera. How can a star be older than the time it took for the universe to create it? This paradox forces a re-evaluation. Perhaps our stellar aging models are subtly off, and the Methuselah star is slightly younger than it appears. Maybe it acquired its unique composition through a rare and forgotten process. Or, more dramatically, perhaps the universe truly is older than 13.8 billion years. This could happen if the early expansion was slower than our models assume, which would be the case if dark energy or exotic neutrinos altered the universe's youthful growth spurt. The Methuselah star is a silent, gleaming challenge, a single point of light that contradicts our grandest narrative. It reminds us that the age of the cosmos is not a settled fact, but a story we are still learning to read, one where the oldest citizens might hold the key to rewriting time itself. The Methuselah star's ancient light is a solitary beacon from a time when the cosmos was almost entirely dark. For hundreds of millions of years after the Big Bang, the universe was a featureless, expanding fog of hydrogen and helium gas, silent and utterly black. No stars shone, no galaxies swirled. This was the cosmic dark ages, a profound stillness stretching across the void. Then something changed. Deep within the faintest wrinkles of density, seeds planted by quantum fluctuations in the first instant began to stir. Where dark matter had pooled most deeply, its invisible gravity began to pull the primordial gas. Slowly, achingly slowly across millions of years, these clouds of hydrogen grew denser and hotter. They were the nurseries for the very first stars, and their birth would ignite the cosmos, ending the dark ages in a blaze of cosmic dawn. These first stars were unlike anything that exists today. Astronomers call them population 3 stars. They were behemoths composed purely of hydrogen and helium, with no heavier elements to help them cool and fragment. They grew monstrous, some hundreds of times more massive than our Sun. Imagine a single star so brilliant it outshone an entire modern galaxy. Their lives were spectacularly brief and violent. Burning their nuclear fuel at a ferocious rate, they lived for only a few million years before exploding as titanic supernova. These first explosions were the universe's first alchemists, forging the first heavy elements, carbon, oxygen, iron, and scattering them into the surrounding gas. This stardust would become the building blocks for future generations of stars, planets, and ultimately us. But their most profound impact was on the cosmos itself. The intense ultraviolet light from these first stars and the quasars powered by the first black holes began to rip electrons away from the hydrogen atoms that filled all of space. This process, called reionization, flooded the universe with energetic radiation, burning away the primordial fog and making the vast intergalactic medium transparent to light as it remains today. It was a fundamental phase change for the entire cosmos, a great clearing of the air that allowed light to travel freely for the first time. We are now on the cusp of witnessing this epoch directly. The James Webb Space Telescope is our time machine, designed to peer back to when the universe was only a few 100 million years old. Its infrared eyes can see the light from those first galaxies, stretched by the expansion of the universe into longer, redder wavelengths. Every deep-field image it captures is a look back into the era of first light, searching for the faint, red smudges of infant galaxies assembling in the dark. By studying their numbers, their shapes, and the composition of their light, Webb is testing our theories of how structure formed against the relentless pull of expansion. Did galaxies form earlier than our models predict? Does their ancient starlight show the unique signature of those first pure population 3 stars? Each answer rewrites the story of how a smooth, dark universe became a structured, luminous one, revealing the delicate balance between gravity's pull to create and expansion's push to dilute. This grand assumption of a uniform cosmos is now facing its most direct challenge. Is the expansion truly the same in every direction? The cosmological principle, the idea that the universe is homogeneous and isotropic on the largest scales, is the bedrock of modern cosmology. It allows us to speak of a single Hubble constant, a universal expansion rate. But what if that constancy is an illusion? A growing number of astronomers are hunting for a cosmic preferred direction, a sign that the universe is stretching faster in one part of the sky than another. They call this potential anomaly the Hubble dipole. Imagine blowing up a balloon that is not perfectly round but slightly lumpy. As you inflate it, some parts would stretch more easily than others. If our universe has a similar, subtle lopsidedness in its expansion, it would mean the cosmos has a spine, a fundamental axis that breaks the sacred rule of isotropy. The search for this dipole is a meticulous, multi-pronged investigation. Scientists are using different cosmic tracers as their yardsticks, each probing a different era and depth of the universe. One team might analyze thousands of Type Ia supernova, those brilliant standard candles that first revealed dark energy. They would plot their apparent brightness and recession speed across the entire sky, checking to see if supernova in one celestial hemisphere consistently appear to be fleeing faster than those in the opposite direction. Another group turns to even more distant beacons, gamma-ray bursts and quasars. These are visible from the farthest reaches of space, offering a test of expansion uniformity across the deepest cosmic time. The preliminary results are deeply provocative. Several studies have reported a tantalizing signal. They suggest that in one direction, toward the constellations of Centaurus and Hydra, the expansion might be a few percent faster than the average, while in the opposite direction, it appears slightly slower. This is not a claim made lightly, and the scientific community is rightly skeptical. The potential for systematic error is enormous. Could it be that our own Milky Way's motion through the cosmos is creating a false dipole? Are there unseen clouds of galactic dust dimming certain tracers more than others, tricking our distance measurements? Every effort is made to subtract these local effects, but the signal, however faint, persists in some analyses. If this anisotropy is confirmed, the implications are nothing short of revolutionary. It would mean the Big Bang was not perfectly symmetric. Perhaps the mysterious inflattened field that drove the universe's explosive growth had a directional preference, a cosmic grain that imprinted itself on the fabric of space-time. Or it could point to something even more exotic, like our universe being tugged and stretched by the gravitational influence of a neighboring universe in the multiverse, a colossal structure just beyond our observable horizon. A confirmed breakdown of isotropy would force us to tear up the standard model and start anew, building a cosmology where direction matters, where the universe has a memory of its birth written in the very speed of its flight. The hunt for this cosmic lopsidedness is a silent, statistical war fought in observatories and supercomputers around the world, and its outcome will determine if our universe is a perfectly smooth sphere or a subtly warped and wondrously uneven reality. The entire cosmic web, from the grandest galaxy cluster to the faintest dwarf star, owes its existence to a ghostly whisper from the quantum void. This is the most profound connection in all of physics, a direct line from the impossibly small to the unimaginably large. It begins in the first fleeting instance of inflation, when the universe was a seething, microscopic realm governed by quantum uncertainty. In that primordial froth, empty space was not truly empty. It was a turbulent sea of virtual particles flickering in and out of existence, a constant dance of creation and annihilation driven by quantum mechanics. These are the famous quantum fluctuations, temporary bubbles of energy that appear and vanish in a heartbeat. Under normal circumstances, they are ephemeral, vanishing as quickly as they form. But inflation was not normal. The universe was stretching at an exponential, faster-than-light pace. As space violently expanded, it caught these infinitesimal quantum ripples and froze them in place. Imagine a tiny, microscopic wrinkle on the surface of a balloon. Now imagine inflating that balloon to the size of the entire Earth. That microscopic wrinkle becomes a vast, continental-scale mountain range. Inflation did exactly that to quantum fluctuations. It stretched them across the cosmos, imprinting them as minute differences in the density of matter and energy, tiny seeds of future structure in the otherwise smooth, hot soup of the early universe. These seeds were the blueprint for everything. After inflation ended and the universe settled into its more sedate expansion, gravity went to work. Regions that were ever so slightly denser, thanks to those stretched quantum ripples, had a bit more gravitational pull. Over hundreds of millions of years, they attracted more and more of the surrounding dark matter and gas. The denser patches grew denser, the emptier patches grew emptier. This gravitational amplification transformed the faint quantum imprint into the first clumps of dark matter, which in turn drew in hydrogen and helium gas. These clumps merged and collided, building up into the first stars, the first galaxies, and eventually the vast, interconnected filaments and voids of the cosmic web we map today. Your very existence is tied to this chain of events. The atoms that make up your body were forged in stars that formed because of gravity's pull, which began with those quantum seeds. The galaxy you live in, the local group of galaxies it belongs to, all trace their lineage back to a specific set of quantum ripples frozen into the fabric of space during that first trillionth of a second. This means the distribution of galaxies across the sky is not random. It is a fossilized map of the quantum state of the infant cosmos. When astronomers create those stunning maps of millions of galaxies, revealing a vast web-like structure of filaments and clusters, they are indirectly looking at a quantum mechanical waveform that has been blown up to cosmic proportions. It is a staggering thought. The same rules that govern the uncertain behavior of an electron in an atom also dictated the placement of every galaxy in the heavens. This connection is the ultimate validation of the inflationary model, but it also presents a humbling limit. While we know the process, the specific pattern of fluctuations was set by pure quantum chance. Our particular corner of the universe, with its specific arrangement of galaxies and its potential for life, is just one possible outcome drawn from a quantum probability distribution. In a very real sense, the large-scale structure of everything we see was determined by a cosmic roll of the dice in the first instant of time. Quantum dice rolled at the beginning of everything, and yet the game is far from over. We have journeyed through 25 of the most profound unsolved questions about the universe's expansion, from the haunting mystery of dark energy and the unsettling Hubble tension to the possibility of a multiverse and the search for a theory of quantum gravity. We have seen how the fate of all reality hinges on numbers we cannot yet pin down, how the oldest stars challenge our cosmic timeline, and how the very fabric of space may be a grainy quantum illusion. This is not a closed book, but an active frontier, a story still being written in the light of distant supernova and the faint whisper of the cosmic microwave background. The next decade will be a golden age of cosmic cartography. The Nancy Grace Roman Space Telescope will map dark energy's history with unprecedented precision. The James Webb Space Telescope will stare deeper into the era of first light than ever before. Giant ground-based observatories will measure the cosmic web in exquisite detail. Each new instrument is a key designed to turn one of these haunting questions into an answer, and likely, in doing so, reveal 10 new mysteries we cannot yet conceive. The expansion of the universe is the grandest narrative there is, and we are living in the chapter where the plot twists are revealed, so stay curious. Look up at the night sky and remember that the darkness between the stars is not empty but filled with questions. Your wonder is the same impulse that drives the telescopes and the equations. Keep asking, keep exploring, and join us as we continue to unravel the deepest secrets of the cosmos, one mystery at a time.